This is the second part of this homework video. And the next problem we need to work on is problem number 24. And it's the next problem in the series. And number 24 states, a marathon runner completes a 42.188 kilometer course, 42.188 kilometer course, which is just actually a marathon distance converted to kilometers. And he completes that course in 2 hours, 30 minutes, and 12 seconds. There is an uncertainty of the distance traveled of approximately 25 meters. So the delta here, delta A, is equal to 25 meters. And an uncertainty of 1 second in the time. So the delta A for that is 1 second. Calculate the percent uncertainty in the distance. So the percent uncertainty in the distance, what you would do, percent uncertainty is equal to delta A over A times 100. In this case, it's going to be delta A, which is 25 meters, but let's go ahead and convert that to kilometers. So we'll divide that by 1,000. 1, 2, 3. So that's going to be 0.025 kilometers divided by 42.188 times 100. Now this is going to have two significant figures on this. And so if we do the math here, multiply it by 100, we get an uncertainty, a percentage uncertainty of 0.059%. And the second question is to calculate the uncertainty of the elapsed time. So this was the first. The second is to do the same calculation for the elapsed time. So that's going to be delta A over A again, which in this case is going to be 1 second. And I'm going to change all this mess into seconds. And if you do that, so 2 hours is 3,600 seconds per hour. So that's 7,200 seconds plus another 1,800 seconds plus 12. If you do all that, you get 9,012 seconds. Is the same as 2 hours, 30 minutes, and 12 seconds times 100. And if you do the math here, you end up with 0.01% uncertainty for the time. It's actually 0.011096, but because this is one significant figure, your answer here can only be one significant figure. C states that what is the average speed in meters per second? So speed is equal to the distance divided by the time, which is equal to 42. And I'm going to change this from kilometers to meters by multiplying that by 1,000, which just moves the decimal point 3 places. So this becomes 42,188 meters divided by 9,012 seconds. So we end up with an answer in meters per second, which is a most useful answer. And if we do that, this is 4 significant figures and this is 5. So our answer will be in 4 significant figures, and it's 4.681 meters per second. And then lastly, it wants you to calculate the uncertainty of the average speed. And after looking in the book, it turns out the way you calculate when you have two different measurements, you essentially add the uncertainty, the percentage uncertainty together. And so what you would do is add the 0.059 and the 0.01, and you'd get 0.069% uncertainty. And then it says what is the uncertainty, so it's not the percent uncertainty, but the uncertainty if you take that 0.069, which actually ends up, because this is one significant figure, it's 0.07. Again, when you add them, you use the least significant space that's common to both numbers. In this case, it's the hundredth space. And so it rounds up to 0.07%. If you take that and apply that to the speed, you would take 0.07 divided by 100 times 4.681. And so the uncertainty in the speed is going to be 0.003 meters per second, plus or minus. And that is, again, one significant figure. And so this has an uncertainty of 3/1000ths of a meter per second, either up or down. So that's number 24. Number 28, the area of a cylinder is something we're going to need to do this problem. So I want you to remember the area, or the volume of a cylinder. I'm sorry, not area of a cylinder, but the volume of the cylinder is pi r squared, which is the area of a circle, and then it's times h, which is the height of the cylinder, and that leaves you the volume of the cylinder. And you'll need that to do the problem, and that's why I'm writing it down for you. So it says a car engine moves a piston with a circular cross-sectional area 7.5 times 10 plus or minus 0.002 centimeters in diameter, a distance of 3.25 plus or minus 0.001 centimeters to compress a gas in a cylinder. By what amount is the gas decreased in volume in cubic centimeters? Okay, so basically the best way to do that, there's two ways to do that. You can calculate the volume before and the volume after and subtract them, or you can calculate the change in the height and do that. So for A, volume of a cylinder is equal to pi r squared h, which is equal to the total volume of the cylinder. Now remember, the 7.5 they gave you is the diameter, so you have to take that divided by 2, so that's going to be equals pi times 7.5 over 2 squared times the height, which is 3.25. And if you do the math here, you get 143.58 cubic centimeters, which rounds up four significant figures to 143.6 cubic centimeters. So that's the volume of the cylinder. B asks the following question. It says, okay, so what amount is the gas decreased in the volume of the cylinder? And that's the answer on A. B, find the uncertainty of this volume. So again, we add the uncertainties in order to find the total uncertainty. So the percent uncertainty for the first one is going to equal 0.00, I lost the number, hold on a second, 0.002 over 7.5 times 100. If you do that math, you get 0.053%. And then the second one is 0.001 divided by 3.25 times 100. And that's going to be equal to 0.031%. If you add those two percentages together, you get 0.084% as the total uncertainty. And so actually, because this is squared, I'm sorry to say, we have to multiply this one by 2. And that's sort of the trick here, that is because this number is squared, this uncertainty, you actually have that plus that, and then the third one is the height one. So you take 1, 2, 3, so you got 1, 2, 3. So you have to multiply this one by 2. And if you do that, you get 0.14% uncertainty total. And if you take the volume that you calculate and multiply it by the uncertainty over 100, it gives you 0.197 cubic centimeters. So it's plus or minus 0.197 cubic centimeters. Okay, now part of the practice I did this time was to go back on the 4th day and mix in some problems that you worked on the first day in an attempt to keep you from getting comfortable with one type of problem and so mixing the problems up. So number 6 says, what is the height in meters of a person who's 6'1"? Well, if they're 6 feet tall, so 6 times, and it tells you that a meter is 39.37 inches. So we have to change this height to inches so that we can use that conversion. This is 72 inches. There's 12 inches in a foot. And then add 1 more inch, so you have 73 inches. And you take that 73 inches, and 1 meter is 39.37 inches. And if you do the math here, you get 1.8542, which, because this is 2 significant figures, you need to say 1.9 meters. So that's number 6. Number 8, speed of sound is measured to be 342 meters per second on a certain day. What is that in kilometers per hour? So 342 meters per second times 3,600 seconds in an hour times 1 kilometer is 1,000 meters. You do the math here and you get it to 3 significant figures, 1,230 kilometers per hour. Number 9, tectonic plates are large segments of Earth or crust that move slowly. Suppose that one such plate has an average speed of 4 centimeters per year, 4.0 centimeters per year. The question is, what distance does it move in 1 second at this speed? Okay, so you have 4.0 centimeters per year. 1 year is 365.25 days. 1 day is 24 hours. And 1 hour is 3,600 seconds. And if you do all the calculating here, you should get approximately 1.3 times 10 to the minus 9 centimeters per second. Now I got 1.3 times 10 to the minus 7, so you might want to go through your calculator and see what you get, because sometimes they do make mistakes in the book here. But the book's answer is 1.3 times 10 to the minus 9, and my answer is 1.3 times 10 to the minus 7. Actually, the reason we got different answers is I forgot to convert centimeters to meters here. So there's an extra, because they wanted the answer in meters per second. I've got centimeters per second. So this is 1.7. Let me do that again. The answer I got is 1.7 times 10 to the minus 7 centimeters per second, which if you do meters per second, it's 10 to the minus 9 meters per second. You just divide this by 100 centimeters in a meter. I didn't read the problem carefully enough, which is another lesson. You have to make sure you read the problems very carefully. The next section says, what is the speed in kilometers per million years? Okay, so you've got four centimeters per year. And if you want kilometers, you start out by saying there are 100 centimeters. There's 100 centimeters in a meter and 1,000 meters in a kilometer. So if you take 100 and 1,000, there are 10 to the 5th centimeters in a kilometer. Now I just skipped a step here. You can put 1 meter is 100 centimeters and 1 kilometer is 1,000 meters if you want to. It's fine. And then we're going to talk about a million years. This is 1 year, so we're going to multiply this by 10 to the 6 years. And if you do both of those calculations, you get 40 kilometers per million years.